So we have a busy agenda today. We're going to start with a great talk by Chris Maynard from the Met Office. He's a member of the HPC optimization team. And then we'll go into other talks from Jonas and others as we go, and I'll introduce them as we go through. So for now, we'll move straight into our first talk with Chris, if he's here.
Yep, thank you for the introduction. If I click share screen, I should get.
Yep.
Great. Hopefully you're all seeing that. Yeah, so hello, thank you very much for the introduction, and thank you for inviting me to speak. So yes, I'm Christopher Maynard. I currently work at the Met Office. I'm currently acting HPC optimization manager. I also have a position at the University of Reading in computer science, and I'm going to talk today on the automatic generation of OpenMP for weather and climate applications. By way of introduction then, the Met Office is developing a new modeling system for exascale computing. We're replacing a successful, something called the unified model, which does both weather modeling and climate modeling, with a new model called LFRic, after Lewis Fry Richardson, the first person to try a numerical weather prediction. And we have a new dynamical core, which is called Gung Ho. And the reason we're doing this is because our current model, the unified model, is on a longitude-latitude grid. It's a structured mesh, but we have poles. And as you can see, these lines converge as they get close to the poles, and that causes us a problem if our discretization is based on this grid, because we have to do lots of communication around the poles, and that's basically is going to stop us scaling so well as we would like. It's a finite difference code. It's also a semi-implicit numerical integration in time. But it's actually a very good model. It's scientifically very good, and it does have many good computational aspects. So in moving to the new model, what we want to be able to do is maintain the accuracy that we got by using this orthogonal coordinate system and orthogonal mesh here. We want to maintain the accuracy, but improve the scalability and also the ability to exploit other programming models. So the new model is based on something called a cube sphere mesh, which is shown on the right over here. This is and we're using an unstructured representation of this mesh. In order to maintain the accuracy that we got from this model, we're using a mixed finite element method, but keeping the semi-implicit time integration scheme. There are several things that are quite that are specific to a weather and climate model. We are going to solve fluid dynamics, but we're going to do it in a special way because of the geometry. The obvious thing being it's spherical, or at least very near spherical. But not only that, there is orography, there's mountains, bits of rock poke up quite high into the atmosphere. The other really striking thing about this particular domain is the atmosphere is thin and vertically stratified. There's something called the Kármán line, which is maybe 100 kilometers up into the atmosphere. Below that line, almost all the atmosphere by mass is below that line. And above that line, perhaps it doesn't really behave much like a gas anymore anyway. But it's very thin. So the diagram on the left here is drawn to scale with this atmosphere being 600 kilometers deep. If I drew it 100 kilometers deep to scale, then it's basically just a thin line. But the basic point is the radius of the Earth is much, much greater than the depth of the atmosphere. It also rotates. It's not in thermal equilibrium. There's an atmosphere, there's an ocean, there's ice and sea ice, and there's a land surface, and there's moist, chemical, and biological processes that affect both the weather and the climate. So it's a very complex domain to model. It's multi-component and it's multi-scale. Models themselves tend to be large, of order 1 million lines of code. Certainly the is at least of order 500,000 lines of code. Legacy, they can take 10 or more years to develop, and they can last the lifetime of the model, maybe 25 years or more. But they do undergo continuous scientific development. but they need to run operations and production, so we have naturally very conservative about changing those to keep for correctness. This is just scientifically prudent. So how do we create such a model? How will we program? What programming model would we use? So Fortran is our language of choice. It's a high-level language. You've all heard of Fortran, right? Here is some Fortran, but it's an abstraction of the numerical mathematics. The implementation and the computer architecture is hidden, and we have code, which is just some text which conforms to the semantics and syntax of the language definition. And then we have another computer program, the compiler, which transforms that code into machine code for specific processes. It gives us a nice separation of concerns between, on the one hand, the numerical mathematics, and on the other hand, the implementation and computer architecture. Unfortunately, we then break this abstraction by all the parallel performance and memory features we have to expose, and then we literally hack them back together again with MPI, OpenMP, OpenACC, OpenCL, CUDA, PGAS, SIMD, compiler directives, might use Calcos, because now SYCL's the latest thing. Not only are there a whole list of different things, they're different types of things. They're libraries, language extensions, directives, compiler-specific directives, or language frameworks. It's all a bit of a dog's dinner. Here's the nice API I wanted to be able to write some code that basically looks like the numerical mathematics. And here's the API I've actually got. And the problem, and it's worse than that, because with this mixed programming model, if I don't know what happens if I set this data 3 and then flick this switch over here at the same time, because how do these programming models interact with each other? So this is a bit of a problem. To try and get around this problem, the Met Office is taking a domain-specific language approach to developing the new model. Why? Well, there's basically too many programming models. There's a rapid evolution of diverse computer hardware, and we end up with parallel and optimization code polluting the science code, and so we destroy the separation of concerns. What we want to do is try and restore this separation of concerns between the numerical mathematics and the computer architecture using a layered software approach, which we see here on the model on the right. So we have a high-level code, which is the algorithm code, which is just the mathematical algorithm. At the lowest level, we have individual kernels, which are mathematical operations on sections of the data, and in between we have the parallelization system, which contains the parallel code and all the looping. So we embed this in Fortran. In fact, we're going to use Fortran 2003 object-oriented API to control the API between these layers. And if you write the code to that API, then we can use another application called PSyclone, which is a Python application, to parse, transform, and generate the PSy-layer. And it has its own intermediate representation. So a little bit more about PSyclone. So it's mostly written by our colleagues at STFC Hartree Centre. So that's Rupert Ford, Andy Porter, and Sergi Ciso. I believe there's some other people now working on the project as well. And there's some collaborators from the Australian Bureau of Meteorology, and in fact there's contributors from the Met Office as well, including myself. So we have algorithm code and kernel code. We have a parser that will read this code. Then we can generate the actual algorithm code. We can generate the parallelization system code, the Psy code. We can also do transformations on this on the intermediate representation before we generate the PSy-layer code to do different things. For example, to generate OpenMP. So what does this kind of look like? Well, the algorithm layer is very high level. We have a keyword called invoke, which means do this in parallel. And then the invoke will operate on kernels, which take fields. And here we see a number of fields. And you can have multiple kernels in a single invoke. That gives us a bigger scope for ordering and parallel communication, etc. And kernels themselves operate on a single column of data. The fields are data parallel global fields. The key to making this all work is, in fact, it comes in the kernel, which is where we encode the kernel metadata. We can capture the rich domain-specific information that we need to exploit for parallelism and horizontal looping. So, for example, here we see some of the kernel metadata, where we're going to say what type of arguments the kernel takes, and then the operators of fields, whether they're read, whether they're incremented, what space they can operate on, what's the relationship between them, what they iterate over. And it's this metadata that allows us to do the automatic code generation, and the semantics of this metadata has meaning in the weather and climate model, which is specific to what we're trying to do. So in this case, this kernel is just doing local matrix assembly. So it is going to do y equals mx, where m is has been assembled locally in the cell, and the horizontal looping will be in the PSy-layer. The kernel code itself is actually very simple. It just looks like basically Fortran 90. It's loops, arrays, and maybe some Fortran intrinsics and things like that. So here we see some generated PSy-layer code. We have updated halos, which we're using, which is basically a halo exchange via a library called Yaxt, which basically calls down to MPI. We might get some information from the infrastructure to do with coloring, so that's loop ordering. I'll tell you more about coloring in a minute. Here we see the OpenMP workshare across all the cells in the color, and then there's the actual kernel call itself. So I thought I'd take you just a little bit through how PSyclone does this. So to start with a single kernel invoke, it gets a schedule of things it generates from the parsed code. It generates a schedule of things it's going to do. So in this case, if there's no, if the distributed memory is switched off and there's no other transformations, it's just going to loop over all the cells in the domain and then call the kernel. If we apply the distributed memory transformation, then based on that kernel metadata that it's just read, then it can decide that it needs to do halo exchanges on the fields that are coming in to make sure they're up to date first. Now the loop order goes to the last cell in the halo, and then it calls the kernel. So we need to generate some OpenMP as well. OpenMP is generated by a simple Python script to apply the OpenMP transformation. We can apply this to the whole model. We can apply it as fine-grained to a single file or even to a single invoke. And here's the OpenMP script. So pretty much we just say it's pretty much this just does these three things. We import 3 sets of transformations. We need a coloring transformation, the OpenMP loop transformation, and the OpenMP parallel transformation. So we go through the list of all the invokes that's been generated by PSyclone, and then for each loop we need to check some information about the loop itself to see whether this particular kernel can be done, whether it needs to be ordered or unordered. So this is for correctness, we have to color or not color, and so depending on what space the loop's over, we have to color or not. And then we can apply that transformation, and then we do the OpenMP transformation itself, loop over colors, and then put in the OpenMP itself, and then we can print the schedule and see what we've done. So the transform schedule for OpenMP now looks like this. So again, we've got the distributed memory halo exchanges first. Now the loops over the number of, we have a loop over colors. Then we have the OpenMP directives, and then we have for each cell in the color, we're going to do the OpenMP loop across that. And here's the generated code we saw just now. So that's the basic way things work, and with that we're able to generate OpenMP for the whole code, and so we don't actually handwrite OpenMP at all. But we can now look at improving the performance of things. So, for example, here we have so with this finite element approach, we have a degree of freedom that might live on a cell edge. Now, if that space is a continuous space, then that DOF is shared between 2 cells. If that cell those two cells are across a distributed memory partition boundary, then we might have to think a little bit carefully about how we do this. So in this case, this is the own cell that belongs to the partition, and this is the halo cell for a partition. So this degree of freedom to calculate its value, we receive a contribution from both the owned and the halo cell. Now we could just do all the owned computation and let the neighboring partition calculate the values for this cell and then communicate them, and that would give us the correct answer. But we can try and do better than that. We can now try and do redundant computation of the contribution in the halo to the shared DOF. It's redundant because it's done by multiple processors, but it does mean we can do less communication. And not only that, if we did it with MPI only, for example here, 4 MPI ranks, these all have halos. If I do it with a hybrid mode, so for example, 1 MPI task, which has 1 big halo, and then I have 4 OpenMP threads, and so the data is split between those 4 threads, the boundary to area scaling means that if I do redundant communication, there is less work for that redundant communication for the OpenMP if I use OpenMP threads. So here's a scaling plot to show that. So this is for the matrix vector kernel I showed you just now. So basically what it's saying is the time spent in the matrix vector kernel. So it's on a C228 mesh, so that means each panel of the cube sphere is 288 cells by 288 cells. It's 30 levels. It's running on 96 nodes of the Met Office Cray XC40. So it's a medium-sized problem, shall we say. This is done at fixed resource. So 1 OpenMP thread is 36 MPI ranks per node. 9 OpenMP threads is 4 MPI ranks per node with 9 OpenMP threads per MPI rank. And as we can see here, that as we increase the number of OpenMP threads and decrease the number of MPI ranks, it takes less time to do that calculation because the redundant computation favors more threads. The red and the yellow sticks, that's just a plot that has another. The optimization here is just an MPI comms environment variable, so it's not relevant to what we're talking about here. So that all works very nicely, and that all sounds great. So, but the code is undergoing active science development, and that means we can have changes to the API required. Now they're not supported all straight away. We have to do some work in Cyclone if we have to do a new thing. So we can have a way of having handwritten code in the PSy-layer, which we call SycleLite, so that we can still do science development, and then we go away and fix the API and the code generation. So the rules for this is MPI only, and then we will extend the API to generate the OpenMP. So for example, here we see some advection code, which is under development, and is not yet supported by Cyclone. So this is uses a handwritten PSy-layer that has MPI only. And as you can see, of course, it doesn't scale at all with an OpenMP number of threads because there's no OpenMP in it. So it spoils the scaling. So taking this approach, we have to do work, but we do the work in a much more structured way. But we can go further still. So again, we look at this partitioned cells, and we have the same degree of freedom on a shared boundary in partition 1 and partition 2. And so we have this idea that the cell in partition 1 owns the degree of freedom, but for the cell in partition 2, it's an annexed DOF because it's repeated. We also have to do point-wise computations. For example, we might be setting the field to a scalar value, in which case we want to loop over the DOFs, degrees of freedom. Looping to the own degrees of freedom means there's a halo exchange required for the partition 2 to have the correct value of that annexed DOFs. However, we can now do another transformation in Cyclone where we change the loop to include all the annexed DOFs, and that results in a small increase in redundant computation, but a large reduction in the number of halo exchanges. And of course, we can then apply OpenMP to that redundant computation. So here we again see some more generated PSy-layer code, this time for the matrix vector. and as you can see, we're going to set the value of y to 0 before we go into the matrix vector, because in this case it increments into the value of y. So for this particular calculation, we need to set it to 0 first. So this has just MPI in it, and so we say, okay, let's do the halo exchange to get all those degrees of freedom correct. And same for x, and then we do the loops, the last cell in the halo, and then we do the actual, call them the matrix vector kernel. If I do the transformation, I can transform the loop to now do annex DOS. So the first loop here, we looped the last degree of freedom in the halo. So we're redundantly computing into the halo, and then this reduces the number of halo exchanges because there's no halo exchange on Y. We can also put OpenMP threads around this to reduce the cost of the redundant computation. And then we can see other things here. So this particular matrix vector routine is colored loop order because of the shared DOFs. So we cannot fuse this loop with that loop, because this one just loops over the degrees of freedom and this one loops over the cells in a particular order to get the correct answer. So having done those things, using the annex DOS and redundant computation, that gives us about a 60% reduction in the number of halo exchanges. And we've seen that if we do redundant computation with OpenMP, then that scales better using the OpenMP. We can also have a look at what happens to the MPI communication as we increase the number of OpenMP threads. With fewer MPI ranks, we get fewer but larger messages. And we can see how that affects local communication and also affects the global communication. So here we see the small increase in cost as I increase the number of threads, and I make the fewer larger messages for the halo exchanges. And in this teal color here, you can see the cost of the global sum coming down slightly as I have less MPI ranks to take part in there. And if I add them together, overall the communication costs are fairly neutral. It jumps around a little bit because of the Aries network variability. I'm probably going to run out of time fairly soon, so I'm just going to go through the next couple of bits quite quickly. We have a multi-grid solver, and we use geometric multi-grid, and that has a minimum of 2 by 2 cells per partition constraint for simple partitioning and simple communication better to help with the scaling. But if I use OpenMP, I've got bigger MPI partitions and more flexibility. So that's not helping with performance, that's just helping with setting the whole problem up and making it easier to actually gives us access to a load of more resolutions that we couldn't otherwise run at. We're also looking at how we might use accelerators. So at the moment, PSyclone can generate OpenACC, at least for the NEMA API. We're exploring this for LFRic, but compilers have problems with the Fortran, not with the OpenACC. Tests with single kernels show this work well. We're also testing single kernels with OpenMP 4.5 using offload, which is similar but not the same, but the logic to set it up is certainly very similar. We can also target other programming models, OpenCL and test codes, which we can then feed into the FPGA toolsets. We could also target Cocos or Sickle, although we can't do that yet. Another thought, we have this rich domain specific information captured in the PSyclone intermediate representation. How can we let a compiler exploit this directly for optimization? We have other collaborations looking at getting things going with the GPU and using other code generation tools like the Claude compiler. So I'm just going to get to my conclusions then. So the exascale computing, we have the exascale computing software challenge. How can we maintain single science source for code for different programming models needed to exploit diverse computer architectures? We're using a domain-specific language for the Met Office to restore the separation of concerns, exploit the rich domain-specific information that we have in the model, and generate different code for different processor architectures. This also allows us to have productive development of science code. I've tried to show you there's an interplay between the algorithm and the programming model. For example, we're exploiting redundant computation and thread scaling to improve the performance. And just for the record, here are some papers, which I'm not going to go through, but that's in the talk if you want to look up what we've been doing in more detail. And I'm just going to leave you with this, because this is a simulation of something called Aquaplanet, which is a world which has no land, but just ocean and clouds and water. And that's a simulation using the new model. And I think that's rather beautiful. Thank you.
Thanks a lot, Chris. That was a really interesting talk, and nice to hear about all that work. There's a question come in. I wondered if you'd be able to answer it. It's from Jamie Quinn, and they ask, is the DSL in LFRic expressive enough to allow for non-CFD operations, such as coupling to other codes or data assimilation?
We're looking at how we extend things. So at the moment, no. So for example, the dynamics is finite element, but a lot of the physical parameterizations will remain finite difference codes. So we're looking at how we extend into that to keep things working. On the face of it, it's quite simple, but then things get a little more complicated. The issue, of course, with being domain specific is if you make your domain too big, it's too difficult, but if it's too small, it's not useful. So you have to kind of get the size of the domain kind of right. So we are looking at how we extend things to do more things. So we have a project looking at how we might do things with DA. So for example, you might think about trying to do things with an adjoint linear model. If you can parse all the code, you could then try and do automatic differentiation. In principle, that's quite easy. In practice, it's very difficult. That's kind of an exploratory project to see what we could potentially do. So yeah, that question goes to the heart of what it means to be domain specific. Using a DSL approach, which is you get a lot of benefits, but some things you also have to do some extra work as well. So yeah, it doesn't do everything by a long way yet, but we're looking at how we extend it to do more and more things.
That's great, thanks. There's a question come in on the Q&A, but in the interest of time, are you able to answer that by text, Chris, while we get the next speaker up?
Yeah, sure. Actually, there's a question from Mark. I can type that one. Yeah.
Fantastic. All right, thank you very much. If we were in person, we'd obviously give you a very loud round of applause. So you'll have to imagine one for today.